So we can do better, but we need more control over ownership rules. And this is what ownership system allows us to do. Ownership system now tells us that a piece of code, some code structure, can declare if it needs ownership or not. And it will say that it is caller responsibility, so someone who calls this code, to give that ownership. And this can happen in two ways. One way is to give it its own ownership, which is called the transfer of ownership, or it can retain a parameter and pass it to this piece of code while still keeping its own ownership if it needs it. And this leads us to Swift's default ownership rules. So Swift default ownership rules say that functions do not take ownership of their arguments, and initializers and setters do take ownership of their arguments by default. We can change this behavior, as we will see later. Thank you everyone for coming, and welcome to this presentation about Swift ownership. If you didn't know, this year we are celebrating 10 years of Swift, and I think a lot has happened in those 10 years, but we can all agree that today Swift is a very successful application programming language. There are many iOS and macOS apps that use Swift, and Swift has become pretty much the default choice for starting projects on those platforms. But there are some very interesting developments outside of application programming. Yesterday we had two talks about command line Swift. Today there was one talk about Swift assembly. And also Swift on server is gaining a lot of popularity. But we are also seeing a number of movements for other platforms. For example, in this project, author describes how you can use Swift and in Swift UI style write applications for Linux platform. And also, very interestingly, the browser company, they documented their journey on how they built their browser Arc in Swift using C++ interoperability for Windows. I believe that is in beta or alpha version right now. But most recently, Apple has published this vision document for embedded Swift. And there they lay out a vision on how can Swift become successful embedded programming language. Now, at the same time, they are working on this special compilation mode for embedded Swift. And while it's still quite early, we are already seeing a number of interesting projects that are using that new embedded mode to run on various microcontrollers, such as this one with Raspberry Pi Pico, or this one with Panic's Playdate console. And all of this is not out of nowhere. Apple's plan for Swift has always been for it to be used across the full development stack. And they mentioned this numerous times. For example, in this WWDC session, they say that the vision has always been for Swift to be scalable, used for everything from high-level scripts down to bare metal environments. And to prove that they are serious, in the very same session, they announced that they are using Swift in their secure enclave processor. Now, the story with low-level Swift is somewhat more complicated. Apple has always advertised Swift as a fast language. They say that its performance is on par with C-based languages. And that is to a great extent true, but in many cases it is also not true. Under some special circumstances, when you really need to tune performance, you need to drop and use a set of unsafe APIs. And this is not very ergonomic for use, but when choosing Swift for your low-level project, it doesn't make Swift very attractive compared to already established programming languages for those platforms. But the good news is that Apple understands this, and in this document called Swift Ownership Manifesto that they published in 2017, they say, Swift's current tools for fixing the problem are relatively poor, referring to performance problems that programmer might encounter. A programmer can fall back on using unsafe pointers, but this loses a lot of safety benefits and expressivity advantages. Later on, this document lays out the vision on how can Swift become successful low-level programming language, and it breaks down the features to do so while still remaining ergonomic for use. And finally, with the release of Swift 5.9, some of the major features from that document were released. Probably the major one, non-copyable types. We've heard high-level application in yesterday's talk about this from Alex. Consume and copy operator. And finally, consuming and borrowing parameter modifiers, which will be the topic of our talk today. So these are features that make Swift's performance predictable and still ergonomic for use. Okay, so our agenda for today is first to explore problem space, see some use cases where predictable performance is important. We will look into why Swift's performance can be unpredictable, performance of idiomatic Swift. We will look into the idea of ownership, what is it, motivate the need for it, which will lead us to Swift's default ownership rules and how they work. And finally, we will address new parameter modifiers from Swift 5.9 and how can they help us address issues that might arise from default ownership rules. But before we start, a little intro about me. I've been doing iOS development for about 10 years. For quite a long time, I've worked for a company called Novaston Media. We worked on a messaging app. And I was exposed to a lot of architectural decisions and automated testing during time there, so I got to love this. For the past few years, I've been working mostly on music apps, so I got interested in audio development. And most recently, I had some opportunity to do some reverse engineering as part of my work, which I very much enjoy. Some of my journeys with this stuff are in my company's blog, and the company I work on currently is called Infinum. We are a software agency. We work with many big clients, some of which you can see here, but we also work with some smaller startups. We are based in Croatia. Our main office is in Zagreb, but we have offices all around the world. And as a software agency, we get to work on a lot of apps, and one of them was this app called Prime Multitracks App. This is a music app that allows bands to feel missing instruments that they don't have in their bands. And it also allows band leader to control various behaviors of the app in real time. Now, there were a number of features that were interesting during the creation of this app, but I would emphasize one of them, which is called real-time transitions. And in order to implement these feature correctly, you need to switch, the app needs to switch from one song to another song in real time at a very specific, precise moment in time. And in order to do this task successfully, programmer needs to react to some real-time event in a typically very short period of time. And for very low latency systems, this is not the case in this app, but that time can be less than 1 millisecond. And failure to do so would result in some kind of audio misbehavior, such as glitch or crackling. And in any kind of live performance, this is unacceptable. So this is a very constrained environment, and in order to create successful app, in these critical pieces of code, you are not allowed to block. You should not do any I/O, no networking or database operations. But also, you are not allowed to take allocations or take locks, because the behavior of that is unpredictable. And to summarize, predictable performance is the key for making these apps successful, basically. Now, this task is usually done in C or C++ traditionally, but I got interested if Swift can be used to achieve this task, and this is really what led me to this journey to investigate this topic in more detail. Okay, so that is one use case, real-time audio programming, where predictable performance is the key. Some other use cases are some low-level, such as operating system kernels, device drivers, embedded devices, which are constrained by various factors as well. but also game engines, and really any kind of real-time system where reacting to event in timely manner is very important. And just to address application development, predictable performance is not a common topic in application development, but I think it's not that unusual that you have some critical piece of code where performance is critical and you really need to tune it in. So it might be relevant there as well. So what is the problem with usual Swift? We said that we can use a set of unsafe API to achieve good Swift performance, but why can't we use idiomatic Swift? Well, I want to motivate this with this example. So let's say that we have this array with 100k elements, and we want to shift it to the right. And after that, we just print some random elements from the array. Now, this shift function can be implemented like this. So you have mutating func shift, and you iterate through elements, calculate next element, and update current element in the current index at the current element. And if you run this code runs pretty fast, 0.069 seconds. But if you go and do a simple refactoring, such as this one, where we only thing that we do is we extract self into temporary variable and calculate next element out of temporary variable, and you run this code now, this runs in 1.7 seconds, which is 25 times worse than previous example. And this is just one instance of whole class of problems that Swift, idiomatic Swift might suffer from. The nature of Swift, high-level nature of Swift, and memory safety that Swift aims to achieve makes certain performance aspects of it quite challenging. And this is what we see there. But for our discussion here, we will focus on a few things. So one is arc traffic, automated reference counting traffic, which is what our previous example suffers from, as we'll see later. Another one is excessive copying, and the solution for excessive copying in Swift is generally to write copy on write data structures, which will not copy on, on when you pass them around. Unfortunately, copy on write data structures, they do have value semantics, but they are reference counted, so they really suffer from the same problem as outlined in the first point. Okay, so some goals for this talk are, I'm primarily application developer myself, and it was very important for me to understand this topic from high level, to understand high level concepts. So I don't want this to be detailed exploration of certain features. I want to provide a high level overview of the topic. And I want to challenge you to think about the ideas such as ownership more explicitly. And finally, there will be a bunch of benchmarks. So I want to build intuition about ownership rules and their performance impact. So what is ownership? Instead of providing definition right away, what I would like to do is to start with this example. So let's say that we have this simple C function intentionally named ambiguously send, which accepts an array of integers and the number of elements, and it does something with them. It can send them to network, write them to disk, whatever. Now the question here is, who is responsible for destroying memory of this array? Is it this function, or is it someone who calls this function? But also maybe a more fundamental question is who owns this object? Is it caller or callee? And this idea of object ownership was recognized quite a long time ago by Core Foundation framework, which in their memory management guide, they say that when thinking about memory ownership, it is helpful to think in terms of object ownership and not memory management per se. And then they lay out some rules on how object ownership works in Core Foundation. So they have create rule, which says that if you create object, you own it. And this is indicated by the naming convention in the API. So cfbag create indicates that this API returns object that you own and you are responsible for destroying. On the other hand, they have a get rule, which says that if you get object from somewhere else, you do not own it and you are not responsible for destroying it. This is also indicated by naming convention and get in API name. Now, if we go back to our example, we can make it better so that we make it clear whose responsibility is to destroy or actually who owns the object. So in this case, we just name it send and own, and we made it clear that it is this function's responsibility to destroy the array. We still need to rely on convention and documentation, so we either need to name function or provide some comment, which is not ideal, but at least we've achieved something. And this really leads us to this simple definition that ownership is responsibility to destroy. And more generally, ownership system is a set of rules or conventions, such as naming convention, for managing and transferring ownership. It can be implicit, where programmer needs to manually handle these rules, such as in C, or it can be explicit, where compiler checks that program spells these rules correctly, such as in what we have in Swift. Now, in Swift, memory management in Swift works quite differently. We are freed from this tactical question of who should free memory, because we have ARC, which simplifies memory management for reference type. And programmer is to great extent freed from thinking about memory management. But ARC itself is some kind of ownership model. It is a model where you have multiple owners. And taking ownership in ARC means retaining object, and releasing ownership means releasing an object. And there is one additional rule in ARC that says that last release destroys the object. And this is what ARC does for us. Now, we can look at this simplified mental model of ARC to understand this. So let's say that we have this class X, and once we instantiate it, we have one owner. If we assign this A to this variable B, we now have two owners. If we have a function that accepts X as a parameter, and we call this function, we now have third owner. And we have little control over what is happening here, but we do have some broad ownership controls in ARC. So we can use vquar c equals a, where we are specifically saying we are not an owner of this object, someone else is, and also unowned. These are generally broad ownership controls that are usually specific to breaking reference cycles, so really tactical controls to, again, to free memory correctly. And another aspect of ARC is performance. If you look at the same example, the ARC traffic that is generated by it is the following. So once we create this instance, we have, object needs to be created, and it is automatically retained. It has retained count of 1 so that it survives. Once we assign this A to B, it is retained again because we have a new owner here. When we invoke function needs a reference to it, so we have another retain. When function finishes, we have release. We now have release since this variable B is not used anymore. And we have now release because A is not used anymore. And finally, since A was last reference, this object X is destroyed. And you can see that this could generate a lot of traffic even in this very simple example. Now, if something like this, as you are passing objects around, as your complexity of the code grows, or if you are calling this in a loop, this can really add up. But to really understand how inefficient this could be, what I want us to do here is to measure performance impact of this single retain operation. And we will do so with this package benchmark tool that, as they say, allows you to easily create sophisticated Swift benchmarks. And the tool is great, I strongly recommend it, but the process here will be the following. It will be 3 steps. The first step will be to set up example where we can measure. And in order to do that, we need a reference type. So we have this one, and we have instance of that reference type. And we need 2 functions. So one function that retains, and another function that doesn't retain, so that we can call them and compare the outcomes, performance outcomes. Now, it is very important to verify that example is set up correctly. Swift is very high-level language, and you can easily introduce some side effect that will mess up with your benchmarks. So what we will do is we will look in the tool called Compiler Explorer, which is an online tool that allows you to, on left-hand side, you can copy and paste your code. You can choose programming language that you want to use. You can choose the version of the compiler that you want to use. And here you can also set compiler flags that you want to pass. And finally, on the right-hand side, you get generated code or assembly. And in our example here, what we can see is that this do something with retain, and on the right-hand side, output of it, generated code, are doing the same thing. So this function only returns. So we will not measure anything unnecessary. And for the function that does retain, we see that it only calls Swift retain, which is also good. So our example is set up correctly. What we need to do next is we need to set up benchmark. And in order to set up benchmark, we need to first decide on scaling factor and choose relevant metrics. Scaling factor is how many times your code will be called in a loop, and metrics are what you are interested in. In this case, what we are interested in is retain and release count, but ultimately we are interested in CPU time that these functions take, as we call them. And then finally, we need to define benchmark, and this is done in this way. So you create this benchmark, you name it, and then in a loop, you call your function, in this case, that does retain, and in this case, that doesn't retain. So we have 2 benchmarks for this specific example. Just a note about this black hole. So this black hole is important to avoid any compiler optimization, so that sometimes compiler can see that our code doesn't have any side effects, and it might optimize it completely away. And finally, we can run this with a Swift package benchmark target, which we set up, in this case retain, and this flag to scale our output. And once we run it, we get this nice table, which contains percentiles, but just to show you important parts, what we see here is that this example with retain, this is scaled metric, so 1,000 is 1,000 retains is scaled. You can see K. Calls retains a number of times, and you can see that our without retain doesn't call retains at all. So this is another proof that we've set up example correctly. But more important metric in this case is the CPU time. So you can see a way bigger difference for call with retain. And if you visualize this in this way, you can see that this is 8 times difference, 8 times improvement for the code that calls function without retain to code that calls function with retain. And keep in mind, this is only for retain. Usually when you retain something, you need to release it as well. So this impact would be even bigger. Okay, so just a short recap of what we've done so far. So ownership is responsibility to destroy. Swift uses ARC for memory management. And this simplified ARC model that we've presented would be inefficient. So we can do better, but we need more control over ownership rules. And this is what ownership system allows us to do. So ownership system now tells us that a piece of code, some code structure, can declare if it needs ownership or not. And it will say that it is caller responsibility, so someone who calls this code to give that ownership. And this can happen in two ways. One way is to give it its own ownership, which is called the transfer of ownership, or it can retain a parameter and pass it to this piece of code while still keeping its own ownership if it needs it. And this leads us to Swift's default ownership rules. So Swift default ownership rules say that functions do not take ownership of their arguments, and initializers and setters do take ownership of their arguments by default. We can change this behavior, as we will see later. So this is a set of trade-offs that Swift or Swift compiler team decided that is good one for default ownership system. This is hidden from us. You usually do not need to think about this. And just to show you how this looks in Compiler Explorer, so what we can see here on the left-hand side is we have a simple function that accepts a parameter of type x. We instantiate it and call this function. And if I hide some unnecessary details, you can see that this instantiation corresponds to this Swift alloc object call, and that invocation corresponds to this call to output.test. And you can see that there are no retains. So since functions do not need ownership, or caller is not responsible to retain argument before invoking function by default. On another hand, for initializers, you can see that generated code is a little bit more complicated first, but more importantly, we see the same pattern. So we see a Swift alloc object, we see invocation of this initializer, but most importantly, we see that caller of this code, this main function, calls Swift retain. So initializers require ownership by default, and caller is responsible for passing that ownership. Now you might ask yourself, what if function needs ownership? What do we do then? Well, let's look at the example. So what we have here is a function on the left-hand side that it accepts parameter x and it assigns it to this local, to instance variable of this class y. So this function, in order to keep this instance variable, it needs ownership. And what you can see in generated code is that the function itself will, in this case, retain this argument. But hold on, you might ask yourself, if function only retains when it's needed and doesn't retain by default, why initializers own by default? Wouldn't it be better if initializers only retain when needed? And the answer to this is in this sample, where we have our class y, which has initializer, and we have this kind of factory pattern that creates this y. So we create x and we pass this x to y. So we just create x to pass it to y. And what you can see is that this Swift alloc object is called as usual, and there is a call to initialize y, but there is no retain in between. And the reason for that is that compiler sees that it can forward ownership of x to initializer of y. Okay? So it is important to annotate, in performance critical code, it is important to annotate parameters in the best way that they can be annotated. So if function requires ownership, if you annotate it that it requires ownership, compiler can see opportunities to optimize code. But I mean, since Swift has default ownership system, there are cases when these defaults are not right. And what will happen in those cases? Well, in those cases, what we'll see is unnecessary arc traffic. So we'll see unnecessary retains and releases where it's not necessary. And In that case, what we have is our new parameter modifiers that were released in Swift 5.9, for which we can annotate our parameters with borrowing and consuming and change the default behavior of Swift's ownership system. So these are semantics of this. If parameter is annotated by borrowing, the function does not take ownership of that argument. And if parameter is annotated by consuming, the function does take ownership of the argument, or initializer, or in general, any code construct. Now, borrowing function, we can just compare the default passing convention and what happens when we annotate the parameter with borrowing. And you can see that in this case, the generated code for both functions is exactly the same, which is another indication that Swift's default ownership rules are borrowing. So functions do not take ownership. For consuming functions, the story is different. So what you can see here is the code is quite a bit different, and also you can see the call to Swift release. And this is, again, coming back to what ownership is. So ownership is responsibility to destroy. And in Arc, destroying means releasing. So this function requires ownership of this parameter, so it is responsible for destroying it or releasing. So we can annotate the code correctly, and we hopefully can find some good performance improvements if we do so. And in order to show you the difference, what we'll do now is we will actively work against Swift's default ownership rules. And in order to do so, we will create initializer that doesn't need ownership of its arguments. So it will not store it, basically. And we will create a function that its body consumes arguments. So it will store it somewhere. So function that consumes, which conflicts with the default convention, and initializer that doesn't consume, which again conflicts with the default convention. So for the borrowing initializer, the process is the same as before. We set up example. We have this simple class X. Then we need a default consuming initializer, which you can find here. So public init with X, default convention. And we need another borrowing initializer, we will annotate this parameter with borrowing. And please note that how we use this parameter X that is passed to us. So we don't store it. We just take something out of it and discard X after that. Ideally, we would verify this again in Compiler Explorer, but we will skip that for now. And we need to set up benchmark. So for benchmark, we instantiate this X. Again, create benchmark where in a loop we call initializer that borrows. And we have another benchmark where we call initializer that doesn't borrow. And finally, we can run this in the same way as before, choosing different target that we set up. And what we get is this kind of difference where we see that code that is correctly annotated or for performance reasons is 30% better than the code that is not. And we can repeat this experiment for the consuming function as well. So we set up example where we have this class again. We create default borrowing function, this one, so assign X, which is of type X. And we assign it to instance variable. So keep in mind that this consumes parameters. So the default convention will be incorrect, so to say. And we need another one, consuming function, which its parameter is annotated with consuming. And it does the same thing, it stores it. But now the parameter is more correctly annotated. Finally, we need to set a benchmark. and it is pretty much the same. So we call assign, which consumes, and we call another assign, which doesn't consume. And if we run this in the very same way as before, we get very similar performance characteristics of 30% improvement for the code that is correctly annotated compared to one that is not correctly annotated, or the one that is using default conventions. So these parameter modifiers provide important optimization opportunities. And if we go back to our example, they also, more importantly, really prevent us from doing mistakes. So our example from before, where we had this temporary variable which was messing up with our performance, so this, by default, this shift function is taking self-argument as in-out argument. And if we change this function from mutating to consuming, now the compiler will warn us that we are not allowed to do what we attempted to do before. So what we will get here is that self cannot be used after consume, because this assignment would produce another copy. And I think this is great because it makes our choices as programmers that are performance aware and that need critical performance, it makes choices explicit. So if you really need to do something here, you can avoid this by doing this copy self. But this is clear sign that something can go wrong here regarding performance. So borrowing and consuming semantics can be summarized in the following table. So we have caller and quali and modifier. When a parameter is annotated with borrowing, caller remains owner of that parameter, of that object that is passed. There is no need to retain because caller is responsible for keeping it alive. For quali, there is no need to release because it just receives shared value. Implicit retain is not allowed, so if you, similar to our example before, if you try to pass this value somewhere else that could make implicit copy, this will not be allowed. And explicit retain is allowed with this copy operator that we showed in previous example. For consuming, the caller can either give ownership of its own value if it doesn't need it anymore, or it can retain a value and pass to quali if it needs its own ownership. And on the quali side, quali is only responsible for release. Again, coming back to our definition of ownership, that its responsibility for release, and consuming indicates so. So that pretty much concludes this talk. So some future directions. This is very active area of development. There are a number of pitches, such as this one, where it would allow us to make declarations more tightly control ownership. So you could make it something like borrow let x equals z, which we are not able to do so currently. Another one that allows you to do basically the same, to bind the variable in for loop with specific ownership control. And finally, this one, which is, there have been some recent developments here for non-escapable types. So similar to what we have with non-copyable types, we might get non-escapable types, which allow more tighter control of lifetime dependence. So you can basically, what you can say is that one object's lifetime depends on the other object's lifetime. So those are our pitches. There are some proposals that are in active review, such as this one for non-copyable generics. It is currently not possible to use generics with non-copyable types. This other one, I thought this one was interesting because it's actual use case for non-copyable types. And finally, this one, I think there was some discussion about this yesterday in non-copyable type talk, where when you are doing pattern matching, the value is consumed. So this proposal will allow you to borrow the value, and you will not need to reassign it whenever you are pattern matching over non-copyable value. And I think it wouldn't be fair to finish this presentation without mentioning Rust. I'm not Rust developer and I don't know it, but when exploring these concepts, it comes up very often. And you can see that this section about understanding ownership in Rust is at the very beginning. So you have, basic programming concepts such as functions, control flow, and then you right away have understanding ownership section. And if you look at Swift, in Swift book, not that it's not in one of the first places, it's not there at all. And this is by design. So Swift's progressive disclosure, this is also another aspect of it, that it doesn't expose concepts to developers that are not necessary. Only when you run into some problems or when you need some concept, Swift tries to allow you to do that, but it doesn't do that by default. And while it would be great to see some documentation, at least I think it's great to see that language, in this case Swift, embraces some of its basic design principles. And that was it. Thank you.